Hello, welcome to session number 14 in the series Analog Circuit Design using ADS. This is Anurag Nikam, and last time I had discussed a two-stage amplifier and its high frequency response, and this was a circuit of a two-stage amplifier, two-stage op-amp. First is a differential stage, and then the second one is the common source stage. And what I was talking was that this two-stage cannot drive a resistive load. So whenever you deal with feedback, resistive feedback and all that, you cannot use this two-stage amplifier as is, right? So now I'm going to add a third stage to it, right? So what I'm going to do is I'm just going to go File, Save As, and I'm going to save this as a three-stage op-amp, right? So I'm going to save this as a three-stage op-amp. Okay. So once I have done that, all I need is another stage over here. So I'll first remove VO from here, and I am going to copy the same transistor again. So basically this is there, and this is driven by the same. So this is the load actually, and then this is going to be my source follower, or what you call, so this is going to be a source follower. So this is a PMOS device, and the load is also a PMOS transistor. Okay, so now the swing, really the output swing, so the output node is going to be this one, and the swing would depend on the swing would depend on the overdrive of these devices. So if these devices are large, then the overdrive is going to be small, and the voltage swing would be there. So it is a source follower, right? So if there is the gain of this is approximately 1, right? So the gain is approximately 1. So I can put here a VO. Okay, so just name this as a VO, and I'm going to just do the simulation. So you don't have to do anything, you just do a simulation here. And I'm going to plot VO in dB, and I am going to do a log scale on x-axis. Okay, so this gain is, last time, I'll compare this, right? So this is the gain, and I will compare with the gain of the two-stage op-amp. So a two-stage op-amp is over here. Okay, so you see that there is not much variation. The blue one is a two-stage op-amp, right? But the red one is a three-stage op-amp, right? Not much variation, right? Next thing I want to see is the phase characteristics. So I'm going to say VO out phase, right? And this is my phase characteristics, and I'm going to do unwrap on this one. So let me just do something called unwrap. So the phase after 180 degree doesn't shift back, right? So that's there. So this is my phase response, and let's look at the corner frequencies and the margins, right? So I'm going to put in here a marker. Okay, so I'm going to find the zero crossing. Okay, so roughly here is my zero crossing. So I have around 69 degrees or 70 degrees of phase margin here, right? And the corner frequency I have to look at. Okay, so the corner frequency to the marker. So M2, another marker for the DC gain. So M3. So 61.4 is the gain here, and M2 I want to do as 58.4, right? Yeah, roughly 400 kilohertz is the corner frequency. So now I have a three-stage op amp, right? Instead of a two-stage op amp, and the difference is now it will be able to drive the resistive loads here, right? So you can connect a resistive load here. So this circuit is suitable for that. So now you can make all your feedback circuits with this op amp. So I'm going to basically create a symbol for this circuit, three-stage and two-stage op amp, which I'll use in the later designs. But the main topic, so you have here seen the performance of a common drain, or what you call a source follower, and I'm going to here analyze high frequency response of a common source, common drain, no, yeah, for a common drain amplifier. So I'm going to look at high frequency response of common drain amplifier. Okay, so first thing first is I would draw a small signal equivalent. Okay, so let's say that I have an input which is I in, and then the source has got R in as the internal impedance, so 1 over G in, and then it has got C in as the capacitance. Okay, and then you are going to have CGS. So let's say this is a V in node and this is CGS, and this is going to be my output where I have R2 in parallel with C2. Okay, and this is going to be my source, right? And the drain side, I am going to pull out a current here. So if this voltage is going to be, so this is VO, so this is going to be GM3 times of V in minus VO. So this would be the current which will be flowing in, and this will be grounded. Now the point to note is that if there is a VO, the source is at a higher voltage, then there's going to be body effect, and then there is going to be a GMB term here, GMB VO. So the current is GMB VO and the voltage is VO, so it is equivalent to a 1 over GMB 3 is going to be the resistance here tied to ground. So that can be included in R2. So I can write R2, so I can write G2 is equal to 1 over R2, which will be equal to GDS2 plus GDS3 plus GMB3, correct? Right. And then I can say C2 is equal to CDB2 plus CDB3 plus CL, correct? And then you have got C in will be equal to C source plus CGD3, because if you see the capacitance CGD here would be connected to ground, right? So this will come with C source in C in. Okay, and then you have got R in, so G in is equal to 1 over R in. Okay, so now having done that, let's write down the equations. So VO times of G2, correct? VO times of G2 plus SC2 plus SCGS3, right? SCGS3 plus, okay, so this thing, and then the adjoining term is V in, right? So the adjoining term is V in, so minus V in times of intermediate is CGS3, right? And then you have current flowing into the node minus GM3 V in minus VO, minus GM3 V in minus VO should be equal to 0, Now this thing is going to give me VO G2 plus SC2 plus SCGS3 plus GM3 from this term, right, minus V in times of GM3 plus SCGS3 equal to 0, or I can say VO by V in is equal to GM3 plus SCGS3 divided by G2 plus SC2 plus SCGS3 plus GM3. Okay, so this is something which is an intermediate equation. Now let us look at the input node. So at the input node, all the conductances, so input node is V in, so I would say V in times of all the conductances, which is CGS3 plus S times of C in, am I right? S times of C in plus G in, these are all the conductances, and the adjacent node is VO, so minus VO times of SCGS3, right, and then there is a current which is flowing in, so it will be minus I in equal to 0, right. So now I can substitute V in from that equation. From this equation I'm going to substitute V in. So in this case this would become VO, okay, so VO times of G2 plus SC2 plus SCGS3 plus GM3 times of this term, sorry, yeah, so this term, so that would be G in plus SCGS3 plus SC in times this thing, right, divided by GM3 plus SCGS3 minus of this term, right, SCGS3, right, correct, is going to be equal to IN. So I would have a transfer term which is VO by IN. VO by IN is going to be equal to, okay, GM3 plus SCGS3 divided by, I'll open the brackets, right, so it will be G2 plus GM3 times of G in, and then plus SG in times of C2 plus CGS3, right, so that is the first term here, this is the first term here. Now let's multiply with the second term. So second term is going to be SCGS3 times of G2 plus GM3, right, plus there is going to be S square CGS3 times of C2 plus CGS3, correct, and then the last term is SC in times of G2 plus GM3 plus S square C in times of C2 plus CGS3, right, so that's that term minus, sorry, just one second, okay, minus the second multiplication is over here, so this is going to be S times of CGS3 times of GM3 minus S square CGS3 square, okay, so this is the denominator. Now if I say S square CGS square, CGS3 square, so let me see, CGS square, so this term cancels with that term, and then there is a S CGS3 GM3, so this is going to cancel that term, correct. So now this transfer function AT would be equal to GM3 plus SCGS3 divided by, let's collect the terms, G2 plus GM3, G2 plus GM3 times of G in, is it? Yeah, G in, right? Plus S terms I will connect. So S term I will be G in times of C2 plus CGS3, right? So that is accounted for, and then CGS3 G2, and then SC in, so C in, so this will be plus C in times of G2 plus GM3 plus G2 CGS3, G2 CGS3. So this is there, and plus S square terms. So square terms are going to be C in C2 plus CGS3, C in C2 plus CGS3 plus C2 CGS3, C2 CGS3. Okay, so this is a square term. Now this transfer function AT can be written as GM3 times of 1 plus SCGS3 divided by GM3, right, divided by 1 plus S divided by Q times of omega naught plus S square by omega naught square. So this is basically, okay, so this denominator is a second order equation, right, which allows for you to have a complex pole under a certain condition, right? So now let's see what is this format. Okay, so let's say AS square plus BS plus C is equal to 0. This is a second order equation. Then S is equal to minus B plus minus root of B square minus 4AC divided by twice of A. So let's write this equation. So in this case, B is minus 1 over Q omega naught plus minus root of B square, which is going to be 1 over Q square omega naught square minus 4AC, 4A and C is omega naught square, divided by twice of A, which is omega naught square. So this is the equation for the two poles, which can be complex, which can be real, right? So let's find out a condition on Q when they are real, so and equal. So omega P1 comma 2 would be equal to minus, okay, minus so if I assume this condition that this term is 0, right, so then I have two real poles, right, at the same frequency. So then what am I looking at? Okay, so I'm looking at omega naught square, so omega naught by twice of Q. So this is going to be my pole, and then 0 would be equal to minus of this term, which is GM3 by CGS3, right? So let me just take a pause here. Okay, so this is under a condition that Q is equal to half. In that case, this term will become 0, right? So now this is a condition, when Q equal to half, you have two real poles and there is no question of oscillations or ringing. But now let us consider Q is greater than half. So if Q is greater than half, okay, so if Q is greater than half, right? Then this term which is inside the square root, okay, this term would be complex, square root of a negative number, okay. So now in this case you will have complex poles, so there will be complex pole pair here. Now if q is less than half, in that case what's going to happen is this is going to be real, so you are going to have two real poles, and they are going to be, now it depends on the q which side they are, but they will have two real poles. Now the thing which we have to avoid is two complex poles, because they can cause ringing, okay. So when they cause ringing, so if you give a step input to a common drain amplifier, it's going to have, it's a second order system, so if you give a step input, then it is going to do this and it will have certain settling time, okay. So that's what we talked in the earlier lecture, right? So there would be a certain overshoot here, so there would be certain overshoot here, okay, and that overshoot in a second order system would be given by percentage overshoot will be 100 times of e raised to minus pi divided by square root of 4q square minus 1. So this is going to be your percentage overshoot, okay, and then you can find out the settling time and stuff like that, right? So that's there. Now from this equation, let's compare the two equations, this equation compared to this equation, and put down the natural frequency of this second order system, right? So in this case q would be given by square root of, so from the second term, right? So second term would give, second term here and here, compare that, okay. So this term is equal to g in g2, right? So it will be square root of g in times of g2 plus gm3 divided by this capacitance value, c in c2 cgs3, c in c2 plus cgs3 plus c2 cgs3, c2 cgs3, c2 cgs3, okay. So this will be the q, and then you will have the frequency of this ringing, right? So that frequency of ringing would be given by, this thing should be equal to the second term, okay. So it will be g in g2 gm3, right? So it will be g in g2 gm3 divided by that number, which is this thing, right? G in c2 plus cgs3, g in c2 plus cgs3 plus c in times of g2 plus gm3, g2, sorry about this, sometimes I press wrong key. Oh my god, Windows, sometimes Windows is stupid, too clever is stupid. Okay, let's write this down, c in g2 plus gm3, c in, come on, why this comes up, let's move it to the right, g2 plus gm3 plus g2 cgs3, am I right? or C2 plus CGS3. This is G2 or C2. Terms of S G2 CGS3. Right. Okay, so what did I do? Okay, I did a mistake here. This is omega naught from the third term, and this is your Q. So the Q would be given by, so I will cross multiply this, is square root of G in G2 plus GM3, that will remain, and then this will be a multiplication C in C2 plus CGS3 plus C2 CGS3, right? This thing divided by this term G in C2 plus CGS3, right, plus C in G2 plus GM3 plus G2 CGS3. Okay, now what is the point of doing all this? Okay, now we know that if Q is greater than half, then it is going to have complex pole, it is going to have overshoot and stuff like that. Now the question is, if you want to really damp it, okay, so if you want to damp it, okay, so what I'll do is, for this compensation, I'll show you in the circuit. Okay, so this node, so notice this node, I have to hang a RC to the ground or to VDD or whatever, small signal ground. So I have to have a RC hanging from here to ground if there is a complex pole, and this RC more or less is going to do something similar, right? So I might not need a further frequency compensation on this, but I am not going to derive this because you can find n number of books which derive it, right? So all the point is that you have to sufficiently load the gate node or the input node with R and C to ground so as to stabilize a common drain amplifier. So if you observe ringing in an opamp and the opamp has a final stage which is a common drain, then you have to hang a R and a C to ground. And anyways, you don't know the capacitances, so you would have to put RC here and do a tune, or rather you can just tune this and that will basically compensate, frequency compensate your output stage. So that basically completes the treatment on a common drain amplifier. Okay, you will find lots of books with more treatment on the stabilization or RC. Okay, I can finally put an RC if you like, but it is rarely of any use, right? So I will put here final derivation of R for compensation. R should be greater than C2 plus CGS3 is square divided by CGS3. You can derive this, CGS3 by GM3 times of C2 minus of G2 CGS3. Okay, so as long as your R is greater than that, okay, and then you have a C which is CGS3 times of GM3 C2 minus G2 CGS3 divided by GM3 G2 times of C2 CGS3 C2 plus CGS3. Okay, so you can derive these equations and you can find some number of books where you will find this derivation for frequency compensating a common drain amplifier, so that you have a proper damping, and this is basically a critically damped case. Now, so that completes our treatment of common drain amplifier, and we have a 3-stage op-amp. Next, I'm going to use this op-amps, okay, to design some circuits in the next session onwards. And then as the there is a requirement, I'm going to modify this op amp to be, something different, right? Like for example, if there is a uh, low voltage requirement, then I would make a what you call cascode, folded cascode op amp, or I can make a OTA, for example, and then I would also discuss, if there is a differential out, a differential in, differential out, then I will discuss common mode feedback circuits and all that also in the next sessions as the need arises, right? So I'm not directly going to jump into OTAs or common mode feedback circuits. I'm just going to design some basic circuits using op amps, which people in their second year, third year of engineering they study, right? So it is for those. The next session is going to be there to design some circuits using op amps. All I'm going to do is I'm going to make symbols for these 2-stage and 3-stage op amps. So thanks a lot for this session. Thank you.